Thank you. We have Biodiscerned flight kinematics for articulated flapping systems. I'm the PI of the grant, and Dr. Cordilla is the co-PI. Currently, we have one postdoctoral fellow working with us. We have 4 graduate students. In fact, one graduated, and then another one will graduate this semester. With 2 just passing the qualifiers. And we have 8 undergrads working on different aspects of this project. To give you just an overview of what it is, the primary research question is, can adaptive feedback control of realistic flight robotics be achieved? One of the things that I will basically allude to quite a bit during this presentation is that no one has captured the fully articulated flight of a bird or a bat or something up to this stage. And this is very important. Of course, this is one question out of many, but by answering this, we will be able to reference lots of scientific, basically other scientific unknowns that would also make a big headway in the field. So this is an student artist illustration of the project that we're working on. And the point is that we try to basically become one with nature. Here we chose seagull. The reason being is that we like to make sure that the students are able to, without using very expensive servo systems and actuators, would be able to create something that would be airworthy. We, of course, would look into smaller species, and then hopefully we look into more complex motions as well. But seagull is one of the ones actually at the border of the birds that create a continuous vortex. Whereas if you go to a smaller scale from, let's say, a sparrow and lower size or with bigger size, everyone has a ring vortex. And ring vortex, the flying motion will become like a hopping rather than flying consistently. So a little bit of background about this and where the state of the art is. Lots of experimental observations have been done by my great biologists and colleagues. Normally high-speed camera imagery or limited motion capture has been incorporated into this. And then, of course, we looked into the flapping flights of insects, hummingbirds, birds, and bats. But again, most of these were in context of what the biologists up to this stage have done. I will refer to this in a second. I'd like you to remember this. They basically pinpointed the trajectory of the tip of the seagull flap, or here in this case, pigeon flap. Now, the second part is that the numerical modeling of the flapping motion have been very intricate. They include a very complex moving boundary. We require to resolve basically a full-scale Navier-Stokes, and of course, low Reynolds number creates lots of intricacies, brings lots of intricacies into the motion that we need to definitely identify. However, no one has been able to do a non-time average resolved solution for this. You can't find an instantaneous response for this because your basically boundary is ever-changing. The flapping flight robotics that have been so far achieved by other people are not non-articulated, as I mentioned, normally like insects and butterflies. They have a lot of flexibility in one joint, but not much more active motion in any other flexibility that's inherited into their wing structure. And then there's some limited robotic systems also have been seen previous to that. This was just an example of what happens to the butterfly. Of course, it's very intricate, but when you look into it, one of the colleagues in Japan pivoted a butterfly into a little wind tunnel pilot tube, and then they realized that all this chaotic motion that the butterfly goes through only consists of 3 major motions: flapping, pitching, and heaving. So anything else is a combination of any of these 3. So the research objectives, we'd like to try, in addition to other things, we'd like to try a modern feedback control theory, given that this is basically the age of advancements for electronics and control engineering, to analyze and design a realistic bio-inspired flapping system that basically comply with complex flight mechanics that's seen in the nature. Doing so, we'd like to be able to come up with scientifically verifiable correspondences with what happens in the nature, and then also some understanding that results from the complex flapping motion by incorporating some emerging class of compact, non-contact, and high bandwidth sensors for the synthesis of the flow, and of course development of the experimental rigs that have not been perfected at this stage. The approaches that we like to basically look into, one is using visual servo adaptive controllers, the other one laser servo adaptive controllers, and the ultimate goal of this study is that after we, up to a certain level, get to mimic the motion that we see in the nature, we like to resort to inverse optimization, and we learn how the flight can be done regardless of the boundary conditions and the upstream flow significance properties. Now, if you look at the visual servo controllers, we just use those looking at the robotics equation of motion. We realize that two terms within the robotics equation of motion are unknown if you want to resolve this for a basically flapping creature. One is the unknown aerodynamics. As I mentioned, it's very complex. You need to be able to constantly solve Navier-Stokes, which is impossible. And the other one is the control inputs, that what is the command that the bird will pass on to the muscles, and then the muscle forces as a result will generate a given locomotion that the bird can basically use to fly. Now, in order to do this, remember the previous trajectory that we had. We use that, and then we use also visual servo controllers that are basically mostly high-definition cameras to be able to figure out what are the coordinates in compared to the focal plane of the visual servo controller. It means that you only have one sheet, but you can find the coordinates away from that focal point, focal plane. Then having done that, we would be able to find a trajectory for the system that we've developed. For example, like here. I'm sorry. Was there a laser? It's right there. Oh, sorry. So having done that, we come up with a design of the system theoretically, and of course, I mentioned that we have developed two prototypes, two generations of the bird so far that will be able to capture this essence. Now, we know the motion, the trajectory that we need from the biologist investigation. Now, having developed this, we use visual servos to be able to see if we were able to capture it, and what we need to do to be able to exactly mimic that particular response given a certain initial conditions. Now, the other approach is, now we use laser servo controllers, such as LiDARs and all that, that will give us the entire domain within a space. All the coordinates, it's not just relative to a focal plane, but also you can pinpoint any point in the space. So we're using that as well as a 3D laser system that you place the bird in, when I say bird, we're talking about the robotic system, because exposing the birds to the lasers are basically subject to animal protections, and then we work with Smithsonian to be able to see if we can address that. However, if we have this system and then we place it in a room equipped with LiDAR, we would be able then to figure out exactly where those trajectories are, and then we compare it to what the actual bird does. So this is a representation of generation 1. We use visual stereo vision camera to be able to capture. This is, of course, a bit sped up. That's why you see more flapping frequency that the device does to achieve that trajectory. However, it gives you an idea. Here, I can resolve the domain. I can figure out exactly what point of space that I'm interested in, and I find out the coordinates based on that. It's a great tool for us. I think my slides are a little bit back to front. However, the take-home point is that up to this stage, most mimic flapping flight that you've seen are kinematically inaccurate for complex systems, of course. Our job is to synthesize the rich flight mechanics that has not been accomplished so far. So articulation is absolutely important for us. Then, doing so, we look into the aerodynamics that are major stumbling block for us. We need to, of course, resolve Navier-Stokes solution in the analysis. However, given the fact that the frequency of flapping is more than 3 to 5 hertz, it's not possible, given the state of the art of the controllers, to be able to fed this back into the system to be able to have some meaningful locomotion as a result of it. Therefore, we like to refer to real-time learning theory and allow the bird, hopefully, at some stage to synthesize the field based on the feedback it gets and eventually create an image of what happens and then preempt sometimes even the boundary conditions. So right now, this is a very simple example to show you that how complex the Navier-Stokes can be. This is just a two-dimensional. Now we're working on resolving it for three dimension. Again, this is not time average. It is instantaneous. However, not only this is the problem for us, but also you see that we are sitting right in the middle of biomechanics, science of biomechanics, control theory, and learning and approximation theory. So if we can merge all of these nicely together, we would be able to then make a huge contribution to the science. Now, the data so far, students, of course, thanks to the initiatives that came through Dr. Mueller, they were able to work with Smithsonian. They go there, they inspect the collections, some of the things that are even in the archives, and then come up with our version of how the birds fly. Because we can't handle the basically birds right now at this stage. However, this is just really amazing that after several consultations with Smithsonian and all that, this is the student's representation of how the bird works, a bunch of cardboard put together. But it captures all the intricacies of the wing of a bird, including all the active degrees of freedom that you have. I'm not talking about the flexibility of the wing or anything like this. Now, based on this, we try to see, you realize that there are too many degrees of freedom involved in this. So we try to simplify it to more manageable, in this case, 4 degrees of freedom, 4 stations, 4 degrees of freedom in the bird, to see if we would be able to come up with some resemblance with what the flight mechanics does. Now, going back to what Tuwalski had done, they projected all of these, basically the trajectory of the tip of the wing, which is seen here, and then also the humerus that is down here. Designing the system, reduced system, we were able to theoretically, and then as you saw previously, experimentally, incorporate this, and you see that it seems that it meets all these points. And then we investigated further in 2 dimensions, we realized that, yep, we actually passed all those. I'm sorry, I'm running. We hit all these points with lower degrees of freedom. However, in again, further investigation, we realized that even though we meet some of those points, however, at some points, the wing is not in a practical position. And that cannot work. Therefore, we moved on to developing a higher degree of freedom wing that is now theoretically capable of showing all these degrees of freedom throughout the wing, and then, of course, through the Devanagh and Hartenberg transformation matrices, we were able to figure out what is the relationship of the shoulder to the tip. And then based on that, we came up with something that theoretically at this stage captures exactly what the bird does in one given condition. Now, future research directions, right now we try to incorporate real-time approximations for the bird to basically understand what synthesize the field using adaptive controllers and adaptive estimations. For experimental methods, it's also important for us to be able to find some things that are time resolved, not average resolved. And of course, that incorporates drag and lift and moments that are applied to a closed loop. And then after this, we like to move on to closed loop experimentation. Everything that we've done so far is open loop, but the closed loop would be state of the art in this area. Potential links that we have, we submitted 2 NSF grants for about $500,000. NASA Office of Chief Technologies have been contacted, and then we also entering discussions or having discussions with 2 of these, and then Office of Air Force, Air Force Office of Research would also be another one that will be on top of the list. Now the highlights, we created the first generation, which was called Deadless 4 degrees of freedom in one wing, active motion, basic locomotion. We conducted comprehensive assessment with the bird and then the experiments to figure out exactly recapturing the kinematics. We moved on to the 5 degrees of freedom to fully articulate the flapping motion that we have, and we developed comprehensive open loop control protocols that on their own are state of the art. Of course, we're trying to write the disclosures for this. We have had some smaller grants in terms of in-kind contributions and data acquisition systems from a variety of organizations, and we're hoping for that big sort of break right now. This is a 6-monthly report. We started this project in August of this past year. And then publications, we have one invited paper in IEEE, and also we have several publications. I don't think this is the full list. With that, I'd like to thank you on behalf of all